10, 9, 8. We have a go for main engine start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. Liftoff of the space shuttle, and it has cleared the tower.
It's slow. It is slow. That's the case.
Yeah, you're
Find your touchdown.
Discovery, performance nominal.
Roger, performance nominal. How's the picture coming down, Kathy?
Great picture.
Hello, and welcome to the flight deck of Discovery. We're 260 kilometers above the surface of the Earth, traveling at 8 kilometers per second. If I look out the window, I can see Hawaii. Nice view, huh? What's this? Hey, a macadamia nut. Must be lunch. Banana pudding. This must be dessert. One of the fun things about flying in space is that things float. That's because we are in a free fall orbit about the Earth. The Space Shuttle orbiter, myself, the nut, and my pudding are all falling together. We're weightless. So if this can of pudding is weightless, why did it hurt when it hit my head? The answer to this question requires a little research. Let's imagine that I can send this nut and this can down to a laboratory on Earth. Some catch. As you can see, the can of pudding weighs 100 times more than the nut. But weight can be confusing because weight depends on where you do the weighing. On the moon, the nut and the can weigh only 1/6 of what they do here on Earth. And here in orbit, they both weigh the same, 0. So why is that? It's because weight depends upon the gravitational pull exerted on objects. The Earth is very big, so its gravitational pull is very strong. The moon is much smaller, so its gravitational pull is weak and objects weigh much less. Here in orbit, we're in free fall, and that makes it seem like there's no gravity at all. So objects have different weight depending upon where they are. Well then, what does that have to do with the bump on my head? The answer lies in the fact that even though the pudding can has no weight, it does have mass. Mass is the amount of matter that is packed into an object. All objects in the universe have mass. Weight can change, but not mass. The mass of this nut and of this pudding can remains the same no matter where they are in the universe, even here on the orbiter. The can of pudding has more mass than the nut, so it hit me with more force.
So why have we spent all this time explaining mass to you? Well, it's because you have to understand the concept of mass in order to understand Sir Isaac Newton's 3 laws of motion. And that is what this show is really all about. Newton was a pretty smart guy. About 300 years ago, he came up with the first mathematical formulas to describe things in motion. We couldn't have traveled up here into space without a good understanding of Newton's 3 laws of motion.
So, what's the first law?
Every material object continues in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it.
Couldn't we come up with a simpler way to say that?
An object at rest will remain at rest unless acted upon by an unbalanced force, and an object in motion will remain in motion unless acted upon by an unbalanced force.
Thanks, Professor Astor. That's much clearer.
You're welcome.
Now for a demonstration.
Here's the can of pudding. It's at rest because it hasn't had any force applied to it. So let's apply some force. Now our object's in motion, and it will stay in motion at a constant speed in a straight line until it's acted on by an unbalanced force, like a head. Don't try this at home.
Now on to the second law. It explains the relationship between force, mass, and acceleration. Force is a push or a pull, and we already know about mass. Acceleration is how fast an object changes its speed. Here's our can again. We'll use this little air puffer to apply a gentle force to it for a short time. See, it doesn't accelerate very much. Now we'll apply a greater force. That did it. It really accelerated that time. The greater the force, the greater the can's acceleration. But how does mass come in? The mass of an object affects how fast it will accelerate when a force is applied. If you apply an equal amount of force to 2 objects, the object with the most mass accelerates the least.
Here are 2 cans of pudding, tapioca and butterscotch. If we apply the same force to both cans, they should both accelerate the same and travel at the same rate of speed, right? Well, let's try. What happened? One can seems to have accelerated more. Was Isaac Newton wrong?
Wait, here's the problem. Someone ate the pudding out of one of these cans. Without pudding in the can has less mass, and thus it accelerates more. Newton explained that force and mass are related to each other by acceleration. A force is a push or a pull on the can. More force gives more acceleration. Mass resists acceleration. If we gave the same push to 2 objects, the one with less mass will accelerate more. So here's our equation. On top is the empty can, and below the full one. Force equals mass times acceleration. So Newton wasn't wrong. Okay, who ate my pudding?
Now, what about Newton's 3rd law of motion?
For every action, there is an equal and opposite reaction.
Well, that's very easy to show up here in space. What happens when Lacey pushes against Greg? The force on each astronaut is equal and opposite, so they go off in opposite directions at the same speed. But once again, mass plays a role in it all. Well, let's try that again, but this time let's make it 2 against 1. The 2 crew members on the right have more mass together than our crew member on the left. But the force is still equal when they push off of each other. What do you think will happen now? Well, you're right. Lacey really goes sailing through the middeck. Well, let's see that again, this time in slow motion. Lacey has less mass than the other two crew members, Don and Greg, and therefore he has a greater acceleration and travels faster.
Let's run through these three laws of motion again. An object at rest remains at rest unless acted upon by an unbalanced force. And an object in motion will remain in motion at the same speed and in the same direction unless acted upon by an unbalanced force. The acceleration of an object depends upon its mass and the size of the force applied to it. And for every action, there is an equal and opposite reaction. Newton's three laws of motion are not just formulas or words on paper. They're all